Welcome back, everybody, and welcome to a new lecture in Physics 4.4.11. The topic today is a more mathematical one, where we are going to discuss the background behind the Fokker-Planck equation, and we will also discuss the so-called Langevin equations, which are used as ways to include information about the way a random walker is going to jump in space and sample different configurations, which in our case are positions for the different particles, and how we will use these to place the particle in different configurations and accept the move or reject the move. And this brings us back to the Metropolis-Hastings algorithm, which we derived and discussed in the previous weeks. So the lecture today is going to be a little bit more technical, and perhaps that fits better for a Zoom session like this. And after that, we are going to look at some computational details, because the form of the trial wave function is going to depend when we move into an interacting type of ansatz for the wave function. It's going to include degrees of freedom, like the relative distance between particles, and that requires some special attention when we are going to program the interacting part. For us, till we introduce the interaction piece, when we are setting up a trial wave function, this is going to be a product of single particle wave functions. And whether these are fermions or bosons, the basic outline of the trial wave function is going to be based on a product of single particle wave functions. And these single particle wave functions are in a way easier to implement numerically. However, we need to think of how we want to include the correlations as well. And that leads us to another technical details, which you will find also exposed in the slides here. Now, to quickly remind you of what we did last week. Last week, we throw at you this equation, which is called the Fokker-Planck equation. Now, the first term is the standard kinetic energy, which leads to the standard diffusion equation, whereas the second term, which you see here, is now meant to mimic the way a particle moves under the influence of an external force. We are going to derive this Fokker-Planck equation and try to give you an overarching view of why this quantity, which you see here, P, can be interpreted as a transition probability. Because we are going to use this quantity here in the modeling of the Metropolis sampling acceptance ratio, which means that we need to have an understanding of this function P, which is time dependent and which depends on the positions, and to have an understanding of how we can use this to model the jumping in configuration space in a more intelligent way than the standard brute force approach, which we introduced last week and in the previous week, where we simply multiply the way the random walker jumps with a constant. So the positions in space are, when we have this force, which you see here, they can be modeled with the so-called Langevin equation, which is an equation from classical statistical mechanics. And it is assumed to model the movement of a particle under the influence of an external force, plus some kind of random noise, which varies quickly at a time scale, which is much faster than the variation of the force F. And the equation which we end up to implement when we integrate up this equation, if we are using just, let's say, Euler's method, the simplest way we can implement the update of a position as a function of time here. So time is a kind of fictitious time here. You can think of it as time. And then we would have the new position, which is given by the previous one, times this force constant multiplied with this delta t, which becomes a parameter which we have to fix. And typically we would choose these parameters between 10 to the minus 3 to 10 to the minus 1. These are typical values. You can make the range shorter, but you need to actually test the result as a function of this delta t. If you make delta t too large, then the random walker will jump out of the probability distribution. If you make it too small, it will barely move. So a kind of fine-tuning is normally done with a range of values of delta t. And what you can do then, and which many people actually do, is to take these values, you've calculated the expectation value of the energy, and extrapolate to delta t equal to 0. So you would make a fit of your results and then try to extrapolate. Now, the important sampling which we looked at last time, and there's a set of equations which are being plugged in, there is an assumption of a mathematical form, and the basic mathematical assumption with such a diffusion equation is that when time goes to infinity or becomes very large, then this probability distribution P becomes time independent. So this is one of the basic assumptions about the physical process of diffusion, which, and this is something which we haven't proven, and we're just stating it, you can derive the diffusion equation from a Markov chain. So diffusion and Markov chains are two physical processes which are intimately linked with each other. Now, when you have reached the steady state, then there is a requirement that the left-hand side of this equation should disappear. And that puts some additional requirements on the second derivatives and this force which we have introduced here, which then leads, when we simply go through the algebra, leads to an expression for this F, which in our case is normally labeled the quantum force, because the probability we have is given by the wave function squared. That's the probability distribution for being in a specific position. And then this force can then, if we want to fulfill this requirement, that the left-hand side of this equation has to be 0, under the assumption of a specific mathematical form, we can then find an expression for this force, which we normally call the quantum force. And this is something which we have to program. Now, with that, you can actually solve, and this is one of the reasons why people use the Fokker-Planck equation. You can solve, if we now go back to the equation here, we can actually solve this equation for a specific probability, and that is going to lead to what is called a Green's function here. And this is the quantity which we need to include now, so that in the Metropolis-Hastings algorithm, we are going to have a transition probability, which I'm going to call the Green's function. And today, I will try to give you an overarching view on why we can interpret this Green's function, which is the solution to the diffusion equation with this force F, why we can interpret that as a probability distribution. So what is going to come now is more kind of mathematical derivation of this Green's function by solving the diffusion equation. And we are going to start with the diffusion equation without this external force. Then we will add the external force, and we will go through the mathematics which is needed in order to obtain this Green's function, which will be a particular solution of this diffusion equation. And then we will interpret this Green's function as a transition probability. So there's a long way to get to these equations, but I wanted to demystify some of the details so that you can see why we can interpret this as a probability distribution. And this will make our sampling much, much more relevant in the sense that we are being guided by the trial wave function, which defines the probability distribution. And then with that trial wave function, we can then make, hopefully, a little bit more guided, a kind of more guided jumping in configuration space, which in our case are the positions of the particles. So that means that we are going to define a probability of jumping from X to Y in a time step delta t. So what I'm going to give you now is the kind of mathematical way you reach this understanding. This is going to require, in a certain sense, that you are a little bit familiar with the solution of differential equations with the Fourier transforms, and then the mathematical process of convolution. So if you have taken a course on mathematical methods in physics, these are things which you may have seen. You may have encountered topics like a Laplace transform, a Fourier transform, and then the mathematical process of convolution. So some of these details, I hope they are details which you have encountered. If not, you can just keep this at an overarching level and just see how we can then reach this interpretation of this function g as a probability distribution. In our case, this is going to be a model of the transition probability. So I wanted to also remind you of the fact that when we look at the Metropolis algorithm, or when we are looking at a Markov chain, in a Markov chain, we have a model for the probability of being in a position. That is the probability which we are modeling, which in our case is the wave function squared. But we don't have a model for the transition probability. That means we know the probability of being in a specific position x with a set of quantum numbers, but in general, we don't have a proper understanding, unless for some very, very simple systems, of what is the probability of making a transition from one position x to another one within a given time step delta t. So time here, you can view that as a kind of artificial quantity, but it can also be interpreted as your random walker making jumps in space under specific time steps. So, or time distances. You have your probability at a given time t, and then you jump to a probability at a position within a time t prime minus t, which is our delta t here. Okay, let's switch over to the whiteboard so we can slow down the pace a little bit. And I hope that this kind of review of what we did last week brings up some of the basic and overarching views on what is needed in the coding. So in the coding, you have an example here for this 2-electron case, which we discussed last week. And this example here is just a implementation of this new quantity, the quantum force, which you need to have in your code. And this quantity here is then encoded into this example here. And this is a pretty simple example, but you can follow that one and the basic ideas there when you write your own code. So the hope now is that by this week and next week, that we have implemented both brute force jumping in space and also this importance sampling jumping in space. Okay, any questions so far about the overarching views of things? Okay, so let's move to the whiteboard and look at some of the basic mathematics, which some of you may have seen in a typical course on mathematical methods for physics. So what we are going to look at now is the solution of the diffusion equation. And we have made this basic assumption. We haven't showed the connection between a Markov chain and a diffusion equation, but the basic diffusion equation, if we now replace this quantity p of x of t, we can just replace that with a general function, which I'm just going to call for x phi of x and as a function of time. Then the diffusion equation is given by the following. This is the diffusion equation without an external force. And there are many ways by which you can include this external force. And these become different models by which we are thinking the object is moving under the influence of some kind of external force. So this could be a simple drift term It could be a term which arises due to friction or some air resistance, etc., etc. So what we have now is the famous equation here, where we have the diffusion constant, d, and then we have the second derivative, which then leads to this interpretation in terms of a kinetic energy term. This has normally some initial and boundary conditions. So typically we would have some boundary conditions and initial conditions where we have x, and I'm assuming that I'm just in one dimension now. And then we can easily extend this to more than one dimension. So x, and then we have t equal to 0. And we're assuming that this is given by some initial function, which I'm simply going to call for f of x. Now you can think of this as your initial distribution. Then we have, these are the initial conditions. And then we have typically a boundary condition where we would have in the limit and where x goes to infinity, that this function actually approached 0. And this is going to be valid for all times. So this is a typical boundary condition which you will encounter when you're modeling the physical process of diffusion. And this is actually an important property, because we're assuming that in the limit where x becomes very large, then this probability distribution goes to 0. So we cannot have a probability distribution which keeps large values all over space, because else we would not be able to integrate this up and get a final normalization. So the technique which is normally applied when we solve this equation is to Fourier transform this equation into what we would call momentum space. So the standard technique, just let me repeat that, is the one of Fourier transforms. And I'm now assuming that you may have seen this. If you have taken a course in mathematical methods in physics, you have most likely seen it. And this is a standard technique which has been used over almost 2 centuries. And it allows us to rewrite this equation, which is a second derivative in space, in terms of a simple equation, which is a first derivative in time. And that is something which we can solve easily. So when we do that, then we have that phi of x of t moves over to a function which has been Fourier transformed. And this becomes a function of the momentum, the linear momentum k, which is now a scaled quantity in our case. So we are putting this function phi tilde to indicate this tilde, to indicate that this is now the function in momentum space, and we have performed a Fourier transform from x to k. So my hope is obviously that you have taken a course in mathematical methods, so that you have seen this kind of formalism before. That means that we can transform this equation, which is given first in momentum, in coordinate space, in terms of a second derivative. We can actually rewrite this equation in terms of a much simpler one, which now has the constant d, and then I have k squared, momentum squared, multiplied with the function phi tilde. And this is a function which we can easily integrate. And it's going to have an initial condition, which is also Fourier transformed. So we're just transforming the coordinate space degrees of freedom. So with initial condition, which is now a phi of k of time t equals 0, which is given by this f tilde of k. This equation has then a unique solution, and the unique solution is then given by the following. So we get a solution of phi tilde of k of t, and that is given by the Fourier transform of the initial conditions multiplied with e of minus d of k squared times t. And the last term follows simply from what we had here. Now, if we now want the solution in coordinate space, then we simply need, what we need to do then is to perform a new integral, which is called the inverse Fourier transform. So to find phi of x of t is then given by the inverse Fourier transform. Just let me quickly remind you of what a Fourier transform looks like. So if you have a function, a general function g, so you can transform a function g of k of t, that is given by an integral over all values of x. So there's a function d of x of e of minus I of k of x multiplied with the original function, which was g of x of t. And these integration limits goes typically from minus infinity to plus infinity. And then if you take the inverse one, that is simply taking e to the with an argument ik of x instead of minus ik of x. This is the basic definition of a Fourier transform. Now, what you get then is that this function, being the inverse Fourier transform, is then a function which we would typically write out. So we would have a Fourier transform of this f of x, and this is given by f minus 1, the inverse of that one. This is the inverse Fourier transform of this f of tilde. And we can then find the function pi of x of t by simply performing a new integral. So if we now take a function which is given by, suppose now that we assume that this function is this function f is a Gaussian. So let's now take a simple example here, because this is the one which we are going to use now in the interpretation of probabilities. So the example here is now to assume a Gaussian distribution. So if I take a Gaussian, so that means that I have a distribution where this f of x is given by some e to the minus a squared. So a is just a constant times x squared. This looks very much like our harmonic oscillator wave functions, by the way. If I make this assumption that the initial distribution at the f of x at time t equals 0 is given by a Gaussian, then I know that if I take the Fourier transform, this is not the inverse, of e of minus a squared of x squared, this is simply given by the following expression. I have pi divided by a of e to the minus k squared divided by 4 of a squared. Now I can now define this a squared, since we are dealing with a diffusion. I can replace this with diffusion constant, so I can just put that one to d times t, and then I treat t as a fixed parameter. As a fixed parameter, because we are not performing the Fourier transform on t, but we are performing the Fourier transform on the spatial degrees of freedom. So if we treat that as a fixed parameter, then we can then find that if I take this f, the inverse of it, I'm just setting up the equations, I'm not going through all the integrals. You may have seen these integrations before. So if I take that one, then this gives me the equivalent of minus x squared divided by 4 dt, and this is multiplied with a constant, which is now given by the square root of 4 pi times d times t. So that means that a Gaussian, when I Fourier transform it, stays a Gaussian. A Gaussian either in coordinate space or in momentum space. So if I then do this in more dimensions, if I take the same expression and generalize it to n dimensions, then this expression takes the following form. So I have the inverse Fourier transform of E of minus D, and then I have the absolute value of K to this power of 2 times T here. That is simply given by 1 divided by 4 pi of D of T to the power of n divided by 2. And then I have an exponential here of minus x. And I'm putting vectors now because I'm dealing with quantities beyond one dimension. So this is the distribution here. So this distribution, or this function which you see here, is actually known as the fundamental solution of the diffusion equation. Known as the fundamental distribution and I will come back to why this is so important of the diffusion equation. So you could assume then that if you go back to the equations which you have here, that the original equation, this phi here, is now replaced by this function which we defined as a function of f, which could be a Gaussian. So we could assume that phi is given by an initial distribution, which is given by the Gaussian distribution. Or it could just be a Gaussian. We don't need to plug in a statistical interpretation to that. But we know that the Gaussian lends itself easily to a statistical distribution, to a statistical interpretation. So this solution which you see here is what we would call the kind of basic solution to the diffusion equation. And I'm just going to label this quantity below here. I'm just going to give that a name, minus dt, the Fourier transform of this quantity times t, is something which I will just call for a function s of n, where n stands for the dimension of the problem. And it's a function of x, and it's a function of t here. Now, if I put everything together, what I will have then mathematically is that the solution is going to be given by the convolution of this transformed probability multiplied with this function s of n. So what we have then is that the final solution, when I use the convolution theorem, so then the solution of the original problem of x of t is then going to be given by the mathematical process of convolution, which is marked with this asterisk, multiplied with this function Sn of x of t. And this is a function of x and t. And mathematically, this is written as 1 over 4 pi of dt to the power of n divided by 2. And then I have an integral over all the spatial degrees of freedom, since this is now an n-dimensional object. And then I'm going to have a function, this initial function f of y here. That's my initial condition. And this is multiplied with the exponential. And let's now put that in. So I'm just going to rewrite this one. So this continues. So they have the argument, which is given by x minus y squared divided by 4 dt. And this ends here. This is the argument. And this is then multiplied with dn of y. So mathematically, I can obtain the solution to the problem by looking at or just using the process of convolution. Now, if I have this, so suppose now that this initial condition is actually a Gaussian. So suppose that this f of x is given by some Gaussian, which now has been normalized properly. So suppose it looks like this. I have some constants. So these are constants I just put in here so that I can have a normalization which is equal to 1. There's a constant phi 0, which I haven't defined, e to the minus a times x squared here. So we're assuming now that we have a Gaussian as an initial condition. So this could be the distribution. Suppose now that you are, as we mentioned last time, this very, very simple example, you put a given quantity of milk into your cup of coffee. You could then assume that the distribution of milk molecules at time t equal to 0 is given by this Gaussian. And then what you're interested in is how this probability changes now over time, or this distribution of milk molecules changes over time till you reach the most stable state, or the stationary state, or what we normally call the steady state. So if you do this, then besides, we need to have a normalization. So this is normalized. Let me just say that. This is normalized so that what we have is an integral over all the coordinates. And then I have an f of x, which is dn of x. And this is normalized so that this is given by phi 0. So if we perform the calculations, so I'm not going to go through the calculation of these integrals. This is a technical part which I will omit. I hope you can forgive me for that. Some of you may have seen this before, and you can actually look this up in any textbook on mathematical methods of physics. So what I'm showing you here is a kind of standard exercise when people study Fourier transforms and convolution. So what we will get then is the following. When I perform the integration here, and if you're interested, I can send you the details if you want to look them up, but I'm not going to go through the calculation of that integral here because that simply just involves various tricks with the change of variables and integrating e to the minus x squared. So what we get then is this constant phi 0. We will have a new set of constants which comes from the integration when I perform the Fourier transform. So there's a d of t, and since I'm dealing with a quantity in n dimensions, this has a factor of n divided by 2. And this is then multiplied with the integral I'm going to perform. And it has an exponential. And this exponential goes like minus a, and it contains this y squared. So this is my initial distribution. And then it has the quantity x minus y squared divided by 4 of dt. And this is then multiplied with the dn dy factor here. So you can think of this as you having an initial state, which then transits to phi x of t in a time t. So we can then interpret this function which you have here, this specific function here, as a kind of transition probability. So if we now go back to what we wrote in connection with a Markov chain, so for a Markov chain, let's just set this up here. And this is now a continuous distribution. If I use the Markov chain, then what I would have is something which looks like this for a continuous distribution. I have a function which is now integrated over all of space. I have my phi of y, and this is given by a given time t here, and is normally given by a time t prime, but let's now assume that it's time independent, or it just depends on this time t. And then we can think of this as a function of a probability which depends on x and y, and this time t. And this is multiplied with d n of y. Now, what we can do then is to interpret what you see here. And if we link this with a Markov chain, so we have the original distribution at the time t0. Actually, the quantity which you see here is this quantity here does not have a time dependence. So there's no time dependence. This is our initial condition. So that means that what we are doing now is in a time t, we are now performing a transition from an initial condition to a new distribution. And this is multiplied by this quantity here, which we then can interpret as a transition probability, or the probability of making the transition to a new probability, which has essentially the same mathematical form, but it's multiplied with a transition probability. And if we assume that the initial probability, or the initial function, which we have, the initial condition is given by a Gaussian, then when we perform this integral, we are going to get back a Gaussian. And actually, the integration here gives us a phi of x of t, which is going to be a Gaussian, so it's going to contain this constant. And then I have an a divided by pi, and this is divided by 1 plus 4a dt of n divided by 2 to the power of n divided by 2, and multiplied with the exponential of minus a, which is just a constant, and x squared divided by 1 plus 4a of dt, like this. So what we see is that an initial Gaussian maintains a Gaussian form with its squared value, which you see here, which now goes like 1 plus 4a dt. And that means that it is spreading linearly with time. And the peak at x equal to 0, that drops now as a function of the time to the square root of minus 1/2. So what we see here is that an initial Gaussian, let me just put this down in words, an initial Gaussian remains a Gaussian. That remains a Gaussian. From the remain a Gaussian with a spreading, which is linear in time, linear with t, and the peak, which we see at x equal to 0, that drops with a speed, or diminishes, or spreads out as function of t to the power of minus 1/2, which is seen in this quantity which you have here, and the quantity which you also have here. So that means that your distribution, if you are to look at this at a given initial time, you could now think of having the following. So suppose that the distribution of time t equal to 0. So this would be the t equal to 0 distribution, which is a Gaussian. Then this moves at a given time different from 0. This will spread out as a function which is linear in t. And this spreading out, so the distribution becomes more and more widespread at t larger than 0. And one of the simplest initial conditions which we can think of is a distribution which is sharply peaked at the time t equal to 0, and that could be a delta function. So if I were to have an f of x, which is a delta function, which is now given by some constant phi 0 multiplied with a delta function in n dimensions, then I can actually find that this distribution is then going simply to be, if I do that, then I will find that my phi x of t is going to be given by this constant phi 0. I will have the same factors in front here of d dt of n half, almost the same factors. And then this is then multiplied with a delta function. So I would have a delta in n dimensions of y. And this is multiplied with x, the exponential of minus x minus y squared divided by 4 dt. And this is then given by d of n of y here. And this is a function which I can easily integrate up. It's going to be given by this constant phi of n, and it's multiplied with this function which we defined earlier, Sn of x of t. So that means that if we start with an initial distribution which is sharply peaked at t equal to 0, given by delta distribution, you could think of this example with the milk molecules being dropped in a cup of coffee as just a sharply peaked function at time t equals to 0. So your milk drops are located in a specific position, and then they spread out over time. And this spreading out here is now given by this distribution, Sn x of t, which then again is a Gaussian. So we are having a distribution here, phi x of t, which is given by this fundamental solution of the diffusion equation, which we label as this Sn x of t, which is a Gaussian. So what we have then is a set of problems which can then be defined for the diffusion problem in terms of this fundamental distribution, which is a Gaussian, multiplied with some kind of initial distribution. And then if we want to make the link with the process of diffusion and Markov chains, we know that the Markov chain can then be modeled in terms of an initial distribution, which we have here, multiplied with some transition probability. So that function Sn, which we had, this is a function here, which now is going simply to be given this W by x of t here. So that's the what we normally call a fundamental solution to the diffusion problem. So that's a little bit about the mathematical background, which allows us to think of the solution of a diffusion equation in terms of a transition probability. So that's a kind of, how to say, more overarching argument, which I wanted to give you here. And we can then modify these equations where we can assume that there is an external force. So we could think of now solving an equation which is not exactly the same as we have, but it could be given by the second derivative multiplied with a diffusion constant, multiplied with 5, and this could now be equal to some kind of external force, which is also time dependent. And we could assume that this force F could be time dependent, but it could also be time independent. And that depends on the type of setting which we are interested in. So this is one type of problem which we can get. And we can then, if we now look at the fundamental solution, and we are now going to replace this Sn of x of t with a Green's function. So we can then replace that with a Green's function where we are in an initial position x at a time t, and then we move to a new position y at a time t prime. This is also a solution of the diffusion equation. And you can show that this function, which is normally called the Green's function, this is a solution to the diffusion equation. It's what we call a fundamental solution of x of t, and then we have y at a time t prime. So I know that I'm just throwing these equations at you now, but this is something you can easily look up in any textbook on mathematical methods. So I'm rewriting this in terms of the diffusion constant. So this is the second derivative term of t prime. And this is given by a delta t minus t prime, and then multiplied with a delta n. And this is actually the original differential equation. And then we can use this solution here in order to find this phi of x of t. This can actually be written out as an integral from 0 to infinity when we're looking at time. There's an integral over the spatial degrees of freedom. And then we have a g of x of t of y at a t prime. And this can be multiplied if this force now depends on time as well, in terms of a time t prime and dt prime, and multiplied with a dn of y here. So we can actually show this is fully possible mathematically to solve this type of equation, and we can find an analytical solution if we know the form of the force here. But in general, we do not know the form of this force. So this is the case where we have a force which is not given in terms of a derivative, which is the case we have for the Fokker-Planck equation. So after the break, we are going to go back to the slides, and we are going to look at the derivation of the Fokker-Planck equation. Now, the main aim here with this part of the lecture today was simply to motivate the basic understanding of a Green's function as a solution to the diffusion equation, where we can actually find the solution of the diffusion equation in terms of this fundamental solution here. And this is a Gaussian. And this Gaussian can be now interpreted as a probability or a transition probability. So you can actually say now that this expresses the probability of jumping from y to x. And since it has time here, it represents the time evolution of a probability. And the easiest way to think of that is to think of an initial distribution, which could be sharply peaked around a specific time t equals 0 and x equal to 0. So we could have x equal to 0 here. And then this starts spreading out. And then at a certain point, you reach what is called the steady state. And in that case, this distribution doesn't change anymore over time. So you could now think, and now since we are getting closer to a break, you could think of this as you grabbing a cup of coffee and putting some milk into it. And after some time, these milk molecules spread out and your coffee takes a more latte-like color. So I went a little bit over time because I wanted to set these things in a kind of overarching context. I know that I'm abusing a little bit on expecting you having seen some of these calculations before in a course in mathematical physics. If you haven't taken a course in mathematical physics, I hope you can still see the overarching message that since the process of diffusion is intimately linked with a Markov chain, actually you can derive the diffusion equation from a Markov chain, then we can use the solution to the diffusion equation via Fourier transform and the operation of convolution. We can then show that we can interpret this process in terms of a transition probability or probability multiplied with an initial distribution, which then propagates in time and gives us a final distribution. And this initial distribution is multiplied with a fundamental solution of the diffusion equation, which is a Gaussian. Okay, I went 5 minutes over time, so I suggest that we take a break here. And now with the equation which we defined here, we have now defined a transition probability for the plane diffusion process. So if we collect what we have done, we can then think of this function g, or this so-called Green's function, as a transition probability. So you can read this as the probability of making a transition from a position y at the time t prime to a position x at the time t. So we can compactify this because often we are assuming that the time can be described in terms of the time difference t minus t prime, and that it is reversible when it comes to time, but then it may change as a function of x and y. So when we set up the Metropolis algorithm, we assumed that there was a probability distribution, which we call for t going from j to y in a given time step. And this is the kind of transition probability which we are going to interpret as this Green's function. So here in the machinery which we are setting up, this is now going to be given by this function, which is the solution of the diffusion problem. And in our case, we have an x at the time t, and we start with a y at the time t prime. You will often see this rewritten in terms of g as a function of x and t given, so this bar here, given an initial position y and an initial time t. Now, in general, I will just rewrite this as a function of g of x and y, and as a function of a time difference delta t, where delta t is simply the difference between t and t prime. Now, when we now perform the solution of the diffusion equation in terms of this object, what we will get then is that this Green's function as a function of us moving from a position y to a position x in terms of this time step delta t is then given by this normalization factor, which we put up before the break, 4 pi of d, but now instead of time t, we have a time delta t, and then we have the normalization factor of n divided by 2 here, depending on which dimension we are in. So if we are in 3 dimension, this is 3 divided by 2, obviously. And this is multiplied then with the exponential of minus, and then we have x minus y and squared divided by 4d times delta t. So this is the distribution function. Now, suppose now that we have modeled this one and we are looking at a Markov chain, and we are looking at how a particle diffuses or diffunds in a medium. And then we could simply say now that when we are setting in the Metropolis test, we now want to define an acceptance probability from going from j to I. And this is something which we derived last week, where we have, and the week before, where we take the minimum value of 1 and the ratios of these probabilities. So we have the trial wave function, which is now a psi of t defined in a position x, which is the position we move to. And this is the wave function squared. And then we can think of this being multiplied by this probability distribution. And then we have a x of y of at this time step delta t. But then we take the ratio with the previous time, psi of t of y, no, previous position, sorry. And then we have the transition probability of moving from x to y at the time delta t. Now, if you look at the mathematical form of this transition probability, which we have defined, this g, what can you say about the Metropolis ratio when you use this explicit transition probability? So suppose now that we have found this g, which is the fundamental solution of the diffusion equation, also called the Green's function, or we can just simply interpret that as a transition probability for moving from y to x. If you take this expression here and you look at the ratios, what does the ratio between these two Green's function give us? So feel free to put the answer in the chat or just unmute yourself. So if I take the ratio, if I use this Green's function, which I have here, the term here is just a constant that stays the same, and I'm computing this ratio with this Green's function and the argument here. What does the ratio become if I use that specific transition probability, which is a viable solution of the diffusion equation? Any good suggestions? Or have I put everybody to sleep here? So if you mathematically take this function here and put that one in here, you see now that this is just invariant under the interchange of y and x, which means that if I use this probability distribution in the discussions here, this is just going to be equal to min of 1, and that contains simply psi of t of x squared with psi of t of y squared. So it means that my distribution, which I found, does not give me anything but from what I had before when I did the standard jumping, where I then had assumed that this transition probability is reversible. So that means that going in either direction gives me, when I take the ratio, just gives me 1. So they are just equal. So this is an assumption which we could have baked in, and which normally leads to the simpler implementation of the Metropolis algorithm, which is often also called in the literature just for the plain or just the brute force Metropolis method. Now, if we now want to have a model for this transition probability, we need actually to labor a little bit more. So the equation which we looked at before the break, the equation with a force which is applied to the system, that means that this force here is also going to give us a function, a Green's function, which in our case is as a transition probability is going to be essentially the same as we had for the case without this external force. And this is where the Fokker-Planck equation comes to our rescue. So if I'm going to change the equations now, and instead of solving a plain diffusion equation, if I now solve the following equation of phi of dt of x of t, and then I'm taking the second derivative, so now just looking at this equation in one dimension, just for the sake of simplicity. And then I have a d dx minus f here, where this f is an external force, multiplied with phi of x of t, and f can depend on both x and t if we wanted to. We are just going to assume that this f depends on t on x only, on the position only. If we do that, then we can actually solve this equation, because this is the so-called Fokker-Planck equation. And we are going to derive this now, and we are going to use the slides then to show the derivation of it. But we can then show that this equation here in 3 dimensions, this equation is simply given by G for one particle, which is jumping. When I look at the jumping from x to y as a function of a time step delta t, and this time step delta t becomes a variable in our Monte Carlo calculations. This is given by 1 divided by 4 pi of d of delta t, and now I'm just looking at the equations for one particle, and this is to the power of, if I'm in 3 dimensions, to the power of 3/2, and multiplied with the exponential, and then I have the argument of minus, and now I have y minus x, and then I have minus this d times a delta t, no, sorry, a force f of x, So that's the force in the position x divided by 4d of delta t. So we can show that this is an equation which can be solved, and I can find the basic equation for the Green's function, which then, when I now take the ratios between g of y of x as a function of delta t, and divide that one with the probability of jumping from y to x of delta t, we see that this ratio is different from 1. Now, in the previous case, when we had the plane diffusion equation, the ratio was equal to 1. And then essentially, we were just back to the simpler variant of the Metropolis algorithm. Now, with having this ratio different from 1, it means that now we can start looking at ways to let the random walkers jump in space, which then follow the shape of the wave function. And in the case which we have, this f of x is going to be given by 2 divided by the trial wave function, and I'm skipping the variable x in the right-hand side. This is the gradient of the wave function. So from a technical point of view, what we need now is to evaluate the gradient of the wave function. So these are complications from a computational point of view, which we need to pay attention to. So computationally, so from the calculations of both the energy and the jumping in space, so computational considerations, now we need, for the quantum force, the gradient of the trial wave function. And this x is now a collective parameter for all the variables which we have. So we need that one in quantum force. But this is also a quantity which we will need in the calculation of the energy and local energy. And you will see that when we look at the derivatives, the second derivative of the trial wave function, because that will contain also the multiplication of 2 gradients. So we have to be careful when we now are going to develop a program, because in the calculation of the quantum force, we need a gradient. But in the calculation of the energy, we are actually going to have, when we are setting up the equation for the second derivative, which enters the kinetic energy, so we need psi of t of x in local energy. And that term there will contain, since the wave function is normally going to be split, so this psi t of x is going to be proportional with a one-body part. This is something which we called OB, one-body term, which is what we are doing now in the project. We are calculating the product of the single particle wave functions. And as long as we don't include interactions, this product of single particle wave function is going to be the eigenstate of the whole system. So these will depend on the positions of the different particles. So X is now a container for all the different variables. We have an X1, different particles which are present, up to an X of n, where uppercase letter n stands for the number of particles. Lowercase letter n stands for the dimensionality of the system, as we have been using in the equations till now. So this will contain, this OB will now contain all these single particle states. So this will be a function of x1, x2, etc., up to xn. And this is the part from a technical point of view and a computational point of view, which is the easier one to evaluate. But then we are going to have a part here which is going to contain the correlations. And that correlation part is a little bit more tricky, because that involves at least the coordinates of 2 particles at a time. So we will often have this as a function of xi minus xj. And that clearly complicates the evaluation of the derivatives. So in the equations which you have in the slides, you will find a series of considerations on how you can implement the interacting part of the trial wave function. So this part here, as we discussed last time, is the one where we are making a guess on the form of the correlated part of the wave function. So if we don't have any interactions, the product of single particle wave functions, whether this is for a system of bosons or a system of fermions, and there we need a determinant to set up the anti-symmetry. In this case here, everything is pretty straightforward, but then we need to pay attention to this quantity. And that means that when we are calculating the second derivative, which you see here, we are going to encounter the calculation of two gradients which are being multiplied with each other. So this quantity here, keep that in mind, is a scalar. When you're programming now, this quantity here is a vector because it's a gradient. The local energy and the kinetic energy term is a scalar. So when we are now calculating the local energy, and in particular the kinetic energy, and we are looking at a wave function which has this shape here, then we will end up with the gradient of this one multiplied with the gradient of that one when we take the derivatives. And this is something which we discussed last time. And that's a technicality which we need to think a little bit about when we are going to write the code. But for the moment, we will postpone that till the introduction of the interaction. If you wish to, you can make your derivatives more general so that you can account for the fact that you have an ansatz for the interacting piece as well, or what we normally call the correlation part, which is also labeled as the Hjorth part. We discussed that partly the previous week. So I'm mentioning this a little bit back and forth because these are important computational aspects which we need to take into account. And I should also say that in all these Monte Carlo calculations, the ugly animal, we all love animals, but there are some animals which we love less and some which we love more. So the ugly part in the calculations resides in the calculation of the kinetic energy. Because when we have the potential energy is much simpler because the potential energy in the way it operates on the wave function. So if you think of the potential energy in the local energy, that is going to be given by psi of t, and then I'm going to have a potential energy, and I'm just writing this in a little bit more sloppy way here. But you can see easily that since v does not change psi of t, this becomes simply equal to v. So that means that we need, when we have the potential energy, we are simply going to sum over the energy contributions from the potential energy given the positions of the particles which we have present. So the potential energy part is an easier part to evaluate numerically, and everything which causes problems for us, and that is why we have also looked at the analytical calculations of the local energy, because for the cases which we have, that will also speed up the calculations of the kinetic energy. So if we have the possibility to calculate this quantity here, either through analytical expressions, which is the first task in the project, or through automatic differentiation, this actually helps a lot in the evaluations of these quantities. And as I said, this is in Monte Carlo calculations, the time-consuming part. For the boson case, which we have in project 1, you will see that if you evaluate this numerically with a finite difference scheme, and you compare that with an evaluation performed with the analytical expression for the second derivatives, you will often get a speed up of a factor of 3 to 4. So these are important considerations when we are evaluating the local energy, but also when we are evaluating the quantum force, which now is going to reduce this kind of a simple tuning of a stepping size to a more automatic jumping in space. But the price we pay, even if we don't need to waste many samples, the price we pay is an addition in computational operations, since we have to calculate the gradient of this quantity, the trial wave function. So I just wanted to bring this up because these are important issues when we are thinking of writing the code. So what I will do now is to take the liberty of going through the derivation of the Fokker-Planck equation by using the slides. So this is a more technical aspect so that you can see how this equation appears and how you can derive it. So if you have taken a course in transport theory, this was a topic which was very popular before. And I was exposed to that as a student in Trondheim. We had a 1-year course on transport theory on top of a course on statistical mechanics. And in transport theory, many of the quantities which you see here, like the Fokker-Planck equations, they pop up as natural extensions to the standard diffusion equation. So I know that there are lots of technicality here, but I hope that with the exposing how you can arrive at the Fokker-Planck equation, you can see the wood for the trees, so you have a kind of more overarching view. The thing I wanted to just remind you is the general motivation for why we introduced this Fokker-Planck equation. And the general motivation is, one, is physical. So you can think of now having a force which acts on the system, but there may be some term which depends on the positions. So this could be like a drift velocity, or drift force as we call it. And for those of you familiar with that in mechanics, this is a quantity which we often add in when we are looking at the environment's influence on a system. The main reason for including that one is that technically that is going to give us a transition probability whose ratio between going from x to y and y to x is different from 1. If I just take the plane diffusion equation, as I mentioned earlier, then this ratio is going to be equal to 1. And then it's not that interesting. So what we are trying to find is the one way to compensate for our lack of knowledge of the exact transition probability. And we are trying to make a model of that. And this model is now a model for an external force, which accounts for the way the wave function, the trial wave function looks like. And we know that our probability is given in terms of the trial wave function. So that means that we have a jumping in space which follows the shape of the wave function. And that is hopefully a better way to perform the sampling. So it sounds a little bit strange that we spend all this time on just understanding how the Metropolis algorithm can be changed from the brute force algorithm to something which can automatically take into account the information about the way we jump in space. But this is a better way of doing things because it allows us to jump in space without a brute force algorithm where we have to fine tune a jumping step so that we don't move out of the probability distribution and just then sample a collections of zeros. So I'm going to go back to the Jupyter notebook now. And we will stay with that till the end of the lecture today. Now, what comes now is a set of technicalities which are included in the lecture notes here. And what I wanted to start a little bit with is the basic assumptions which we've been having if we are looking at a continuous transition probability. So what we are saying now is that we are jumping from a time t to a time t plus delta t from x to y. We have an initial distribution here at a given time. And if we go back to the discussions we had about the solution of diffusion equation, this initial distribution could be a Gaussian. And then this function here is just the Green's function, which is the solution to the diffusion problem. And after a given number of time steps, we end up with the final distribution, which is C here when equilibrium is reached. And then when equilibrium is reached, then this distribution here becomes time independent. And we can then assume also that W becomes time independence. Now, when you now look at the derivations you find here, the first part is actually just a derivation of what we did before the break. We looked at the solution in terms of an initial distribution, which is given by a delta function. And then we've made a Fourier transform of the diffusion equation. And then we have the solution here, which is given by this term here, which is just given by the Fourier transform diffusion equation. And then we can find the final distribution, as we discussed before the break, in terms of a Gaussian. So this Wx of t is also called the Green's function. And you can easily see then that this Wx, no, not Wx of t, but this function which you had here is now the, since we start with a delta function, we end up with a distribution here, which is just given by a Gaussian. And you can easily see that this is also normalized if you integrate this up. So this is essentially just a summary of what we had before the break. So what we are going to do next now, if we now look at the general distribution here, which is not so interesting because this gives us a ratio between likelihoods, which is equal to 1, transition likelihoods. But what we are going to look at now is a generalization of these equations. And we are going to assume that we have, for instance, 3 probability distributions for different times. So we would have one here, where we have x as a function of time t, where we start at an initial time t prime. We have another one where we start at a time t0. And then we have one here where we have a time n time t prime here. So they are all given by different times here with t0 less than t prime and less than the final time t. And they can all be expressed in terms of this relation here. So this is essentially what you see here is a transition probability multiplied with the initial probability. And this is the time evolution given by a Markov chain in its continuous form. This is nothing but a Markov chain in its continuous form. And it is also the way we would solve the diffusion equation, as we discussed before the break. Now, this is something you can combine, and this is where these elements from transport theory come in. There is a famous equation, which is called the Einstein-Smoluchensky-Kolmogorov-Chapman, and there used to be a Swedish guy as well, Enskog, but this is the basic famous equation, and this is normally called the ESKC equation. And you can combine these equations, which you see here, using the normalization constant of the equations, and you can then actually relate this transition probability to the transition probability at the previous time, t0. So you can actually develop this transition probability here in terms of an intermediate probability. And this is the equation which is then often used in obtaining the Fokker-Planck equation. So you can transform this equation here. You don't need to stay with the coordinates. You can transform this into momentum space, or if you want to, in terms of velocities. So instead of x, we can have a final velocity v, an initial velocity v0, which is then given by these two transition probabilities. So this is the basic starting point for deriving. This is just one of the ways of deriving the Fokker-Planck equation. So the way you would do then is simply to rewrite this equation, which you see here, by defining a time s, which is the difference between t prime minus t0, and then a time tau, which is t minus t prime, and then this other time t minus t0, which is s plus tau. And we are assuming that these equations here are reversible in time. So we can actually rewrite this equation here in terms of a position x, final position, an initial position x0, and then we have simply rewritten t minus t0 as s plus tau here. So this is just a rewrite of the equations. And then that means that we can actually rewrite the equations which we have here in terms of these two variables. And then we have a dx prime integration here. So this is nothing but just the Einstein, Kolmogorov, Smoluchenko, and Chapman equation. Then we can now make the assumption that this tau is very small. One of the assumptions which we actually make in the derivations of these equations and also in a standard Markov chain, is that this transition probability is time independent. But we assume now that this time is so small that we can then approximate it in terms of a Taylor expansion. So we can perform a Taylor expansion in terms of this time. So we are then going to look at the expansion of this distribution in terms of a Taylor expansion, where we have the first derivative plus terms which go like tau squared. So this is us Taylor expanding the quantity which we have on the right here. So what we are doing then now is that it takes non-negligible values only when this step here is very small. And that's just one of the basic assumptions behind the master equation, which is used in the derivation of a Markov chain, or the basic assumption of a Markov chain, that this transition probability is basically time independent, or that changes take place at very small times. So we say thus that this x changes only by a small amount in this time interval. And that means that we can make a Taylor expansion in terms of this quantity c. So by performing the Taylor expansion of the integrand, which we have in the expression up here, we can then rewrite this in terms of these higher derivatives. And this is just us performing a Taylor expansion of that quantity. Then we can rewrite this equation, which we had, in terms of where we now truncate on the right-hand side. We leave out terms which are higher order in t. So we just keep the first derivative, and then we have the transition probability itself, plus this term here, where we simply have neglected higher powers of tau. And we also use that for n equals 0, we simply get this distribution here due to normalization. So this simplifies things a lot. And then we can continue these manipulations. So we are then going to continue that. And that means we can rewrite everything as you see here. And when we do that, what I'm going to do now is simply to introduce different moments, because you see you have a Taylor expansion, which will now contain c to a given power. So I can define the specific moments here. And this is a more compact expression. And I'm going to call this for a delta x of tau here. So I'm going to simply look at these expansions. And when tau goes to 0, when this becomes very small, we also assume that this quantity is going to 0 more rapidly than tau itself, if this n is larger than 2. So there are lots of assumptions behind the derivations here. But if I do that, I will end up with this equation here. This is the approximation I make in these Taylor expansions. And then by rewriting it in a more compact form, we'll have these moments. I can then at the end replace that one with the different moments which we have defined above. But this equation here now is nothing but the standard Fokker-Planck equation. So where this first term, if we now replace this with the position with velocity, this term which you see here is just the standard diffusion term. And this term here, m1 times the transition probability, if we now go back to the definitions of these moments, we have defined these moments in terms of these integrals. And that means that when I look at these expressions here with some labor, we can recognize this in terms of this force, which depends on the derivative with respect to x. And this would now be the standard kinetic energy term, which we have had before. So this is a way we can derive the Fokker-Planck equation. And then you can replace position with velocities or momenta. And then you have the standard equation or the standard approximations for the Fokker-Planck equation. So that's the Fokker-Planck equation. And how you can derive that. I know that this is a technicality, which is perhaps not the most exciting thing to look at. You can find more information if you go into a standard text in statistical mechanics, where transport theory is included, or alternatively in dedicated texts on transport theory. Or if you go to fluid mechanics, if you're taking a course in more advanced fluid mechanics, you will encounter this Fokker-Planck equation. So it's a way with lots of physics approximation to modify the standard diffusion equation and obtain a term, this term here, the first derivative, which is a term which can be interpreted as a drift term under the influence of an external force. For us, this W, which you see here, is the wave function squared, the probability. And that means that we have the wave function squared here multiplied with this moment. And then we have the standard term here, which is going to be the second derivative of the wave function. So this is a long, long way to go back to an equation which we are going to implement in our Metropolis sampling in order to have a better way to perform the sampling. So keep in mind that the basic motivation for doing what we have done here is simply that we need a better way to perform the sampling. We want to automatize it so that we can have some basic information about the trial wave function. And with that basic information, we are then able to get perhaps a more intelligent way of sampling the different configurations, which in our case are the positions in space. With that, we have a recipe which we can implement, and what you will see is that it's going to give you a better representation of the final result. So important sampling normally always improves the calculations, or it improves the final result. You don't need this ambiguity of having to tune a step size, which allows you to jump in and out of the trial wave function, where you have this ad hoc rule that you tune the step size so you roughly accept 50% of the suggested configurations. The other benefit of doing this is that you hopefully can mimic a transition probability, which is more relevant for the physical process taking place. So it's more physics motivated. Now, when it comes to the jumping in space, what you end up doing then is to use something which is called the Langevin equation. So the link between the Fokker-Planck and the Langevin equations are not that easy to detail. So the way we are going to look at this now is simply to look at a problem where you have a stochastic force, this F, which is this quantum force which we have. And then we are simply adopting the Langevin equations. Now, there's a small digression here. Some of you may have taken a course in machine learning, and you probably then encounter the problems with gradient descent and the approximation of the second derivative in the gradient descent with a learning rate. Now, in order to improve and have some information about how this learning rate changes using the information about the gradients, normally one would introduce methods like adaptive gradients, root mean square propagation, and adaptive momentum updating of the learning rate. But there is a lot of activity actually on using the Langevin equation in updating the learning rate for a training of a neural network, for example. So the Langevin equation simply starts with Newton's equation, and you could consider a particle which is suspended in a liquid, and in its path through the liquid, it will continuously collide with the liquid molecules. And on average, the particle will collide more often on the front side than on the back side. It will experience a systematic force proportional with its velocity, and it's directed opposite to its velocities. And then besides the systematic force, the particle will experience a kind of stochastic force. And it's this stochasticity which is baked into the Langevin equation. And the Langevin equation is something which you will encounter if you take a course in hydrodynamics or if you take a course in transport theory. And it's normally given by simple equations which we put up in the beginning. But you can assume then, starting from the velocity which you have at the time t0, you can integrate up. And when you solve the second equation which you have here, this one, then you can integrate up and you can find a new velocity, or you can find a new position if you want to, which is then given in terms of this quantum force. So this is the basic equation which is normally used to derive the actual implementation of the Langevin equation. So this is something we will discuss a little bit next week. So we will try to wrap up these quantities here next week. And we will also next week say a little bit, if you scroll down here, we will say a little bit about the technicalities when we want to implement the correlated part of the wave function. And this is from a technical point of view, this is the more difficult piece. So as a kind of mini homework next week, I would like you just to take a look at these technical considerations. And then I'm also going to say something about the derivation of the Langevin equation. So hopefully now you have a kind of overarching view of why this Fokker-Planck equation is of interest.